this session, we're going to talk about address resolution. Okay, address resolution. You're probably thinking, definitely most of you will probably be thinking, what is address resolution? So let me just start up a command prompt, and hopefully you guys can see that. So if I go to ping something like, so we all know what ping is. Ping is an echo request to test connectivity end-to-end between my computer and a computer I'm specifying. And obviously I can ping a IP address. So we all should be familiar with the idea of an IP address. And that's a address that we use for communication in IT these days. And you can see that I'm getting replies. Okay, a couple of things. The time, 19 milliseconds. So the longer the time, obviously the slower the network. Okay, so the latency, the lag. And if you remember, we also talked about a TTL, or time to live. If you remember that, potentially on a network where there's some sections of the network which is down, you could end up with a loop that just keeps on going, because the router is just going to forward to the next router, which is going to forward to the next router, and it may never get to the location that's intended to. So every IP packet has a time to live built into it, if you remember when we looked at the headers. So that time to live is how many hops does it go through before it says, nah, that's it, stop, because I'm not getting there. Okay, right now it's saying that I've got a time to live of 16, so it ticks down. If you remember from 130, I believe, it ticks down. Okay, and every router goes through, it ticks down by 1 until it gets to 0, and when it does get to 0, it just disappears. We're all happy with that idea, guys? All right. Anyone not any of this not sounding familiar or something that we spoke about? But if we look at this, there's 4 packets. Okay, so there's it did it 4 times, and each one of them is about 32 bytes. And if you look at this, we've got a reply on each one, and it's 100% received, 0% loss, and basically it's pretty consistent. 90 milliseconds is the maximum, minimum, and the average, obviously. Okay, let's ping somewhere else. Oops. You can see this again is 19 milliseconds, and you can see the time to live is significantly less. That just means it's gone through a lot more routers to get to this Facebook.com than it did for the Google. Okay, but it still got there, and it's still 19 milliseconds, so it's not too bad. But did you notice something? In the first instance, I pinged an IP address. In the second instance, I pinged, what's that called? Name server. That's not name server, definitely not. Jai? It's an address. Okay, if you put it in your browser, it will be a URL, so Universal Resource Locator. The actual accurate word is it's a fully qualified domain name. Okay, it's a fully qualified domain name. If I said, what's your name? And I said, if someone asked me, what's my name? My name is Alex. That's not really my full name, is it? My full name is Alex Zhao, and I live at number 1 First Avenue, Adelaide, whatever. So basically, when you look at a name like that, it tells you who the host is, who the domain is, and what the top level domain is. So we're probably all familiar with that, even if we don't know it specifically. We all know it's something, dot something, dot something, right? Or there could be more even. So obviously the question was, computers use IP addresses to communicate, to find each other. But I just did the same command, but not with an IP address. Why do you think we're not using IP addresses in our URLs, in our browsers, everywhere we use? We obviously can, but why are we not?
Easy for us to remember.
Yeah, absolutely. Yeah.
Difficult to remember.
Yeah, definitely. Like if I had to remember this 8.8.8.8, yeah, like that's pretty easy to remember, right? That's why I remember it, because that's Google's primary DNS server, and I use that as a DNS server if I have problems. But if we look at this one, 157.254.8.35, I'm sure I could remember if I really tried, but that's just one website, isn't it? What about, like forget about Facebook, what about Instagram, what about, I don't know, Hotmail, what about, Outlook? Am I supposed to remember every IP address that's in the world? Okay, in the early days of internet or early days of networking or TCP/IP, that's exactly what happened. There wasn't that many computers, and people used to memorize IP addresses. After a while, they got a little bit more. So instead of actually IP addresses, they actually had a file called a host file. I'll show you. We still have a remnant of that. So it's on the C drive. And it's in the Windows, well, this is a Windows computer, obviously. It's in the Windows folder. And it's in a, sorry, bear with me for a second, System32, that's right. System32, it's in a, so bear with me, drivers, etc. And there's a host file. If I actually open this with a notepad editor, it's basically just a plain text file. It's got literally, this is an example, literally an IP address to a name mapping. Okay, let's actually copy this whole line, and hopefully I can edit this. Let's call this so Alex, and we'll make it something that's never going to be on the internet, 10.10.10.10, and hopefully it lets me save. It's a protected file, so I'll see if I can save it. Yes, it did save it, because you might not have seen, but I upgraded myself to the administrative privileges, and because on these computers, our IT rooms, we are all administrators of the local computer, because there's certain things we have to do that we can't do if we don't have those powers, just like changing your virtual network adapters, for example. So let's open that up again, and you can see it's there. So let's see. Okay, sorry, that's not using that. So that's a name to IP address. Oops, too many. Okay, so it's not looking in my host file for some reason. Maybe I've got the, is there a space here? There might be a space there. So administrator mode, and this is what I'm talking about. That's the UAC, the user access control. All right, so let's see if that changed it. No. Let's get back to, sorry, I'll have to work that out later. But basically, my story, I'm telling you the story, is that when the internet or sort of networking first was invented with TCP/IP, like I said, people used to just remember IP addresses. Then they got a file like hosts, and then they literally had lines and lines and lines of mappings. Okay, lines and lines of mappings. And again, obviously, you can see that this example is statically typed in, isn't it? So whatever I type is wherever it is until I change it. Okay, but we also know that like in the real world, servers go off, go on, IP addresses change potentially. So every time, if first of all, a couple of problems. Any time an IP address changed for a location, then this host file goes out of date, is wrong. Okay, any time, and if you imagine it, this is the entry for one location on the internet. Think about it. How many different sites have you been to? Maybe just even today. Probably at least half a dozen, at least today. But let's say throughout the course of the day, probably literally hundreds. But in reality, there's literally millions of different sites in the world. So there's no way you're going to be typing it all in here. So people used to share these host files, then they just copy each other's host files. But like I said, every time there's a change, there's an update, these host files are out of date. So now, obviously, in my example here, I pinged Facebook, and I can read the next line. This www.facebook.com is really star-mini.cl0r.facebook.com, and the IP address is 157.2408.35. The process of actually getting this IP address is what's called address resolution. Okay, no one computer in the whole world now has all the IP addresses for all the sites in the whole universe. But we still are able to find the IP addresses, obviously. So let's actually show you something else. DNS root servers. All right, so if we look at the DNS root servers, okay, you probably heard of the term, like, I want to register my domain name. Have you heard of that? I want to go get an alex.com and I'm going to register it. But usually you pay a bit of money, don't you? Especially for those popular domains with the .com or the .com.au or something like that. So who am I registering with? Why do I need to register? So it's fine. I can call myself anything I like, but but if I don't register it, no one else is going to be able to find me. It's a bit like having your phone number in the Yellow Pages, or some sort of, if you guys remember the Yellow Pages, but it's some sort of directory. Okay, so the DNS, or domain name server or service, is the directory for IP addresses and domain names. Okay, when we pay money to register a domain name, and you can get some free domain name registrations if you wanted to, but it won't be those popular domains. So let's free domain name register. Like, let's have a look at this. Check domain availability, alex.com. Let's see if it's available. If it is, let's register it. But no, okay, it's not available. Okay, so I can see, like, it's been taken, but these are all the ones I can use instead, which is not very close to alex.com, but that's what you expect. Okay, so yeah, like if I go .com instead, doesn't make any sense, but I'm sure that's available. So the problem is that, oh, good news, I can have that. Well, why would I want that, to be honest? But that looks like the cat ran over my keyboard. But you can register free domains with the .tk, for example. The .tk, so free nom. So find a free domain. So you remember how we said the popular ones like the .coms and stuff like that, they're really for commercial, right? You're legit. If you want to set up a legitimate business, you probably have a .com.au domain name. So let's look up Alex. Okay, look, I can get, no, I can't. I can get No, I cannot get that. I cannot get these. Let's select. Not available. Okay, so these are the costs, but it's not available. Let's garden. Am I interested in garden? That's not even available. All right, I might have to be a little bit more specific. Oh, even that's not available. There's too many. Okay, so let's. Okay. Oh my goodness, these Alexes are very arrogant. All right, so you can tell that you can get these off. These are really off brand type domains. Okay, but you can see that some of these .orgs, .nets, they're more like what you normally see, but you got a whole heap of others. You notice that this .tv, that's a new one. That's not that new, but did you know where this came from? This is an interesting story. You know the TV Islands, Tiwi Islands. They actually got a country called .tv, but they sold it to these ISPs, wherever, so that people could sell the .tv domain name for profit. So that was obviously they weren't using it much anyway. So root service. So when we register our domain name, we are basically putting our domain name in the system so that it can be found. Okay, if we're a legitimate business and we want our business to be able to be searchable and to be able to get to by all our clients, we must register our domain name. So what happens then when you plug in? What happens when you plug in couldn't find it. So someone's registered it. No, let's NS look up. That's my DNS server. That's not. No one's actually. It doesn't give me any details. Maybe someone just registered it. We're actually having an IP address associated with it. Okay, that's what happens. Sometimes there's cyber squatting. You might have heard of that term. Okay, they really register a whole bunch of domain names, then they then go to people like me who wants it. Oh, you want to buy it? You can buy it for this amount of price. But let's go back to something we know. So that's the IP address of google.com. That's our address that we got here. But the process of actually converting that was a human-friendly thing that you remember to an IP address is called address resolution. So what happens when I type in that command, NSLOOKUP, and that stands for name server lookup. So it's basically going to the name server and looking up this thing for me. What happens? What happens to this in the background? So let's go back to my screen and I'll share the video because actually I might be able to do on screen. All right. I think Excel is the best one. No, maybe not. Maybe, yeah, no. All right, so maybe Paint. Okay, so basically what happens? What happens is that there's when we have a client, so I'm just going to make a few boxes. When we have a client computer here, okay, and I need to look up google.com, okay, so in my thing I typed in http://www.google.com, so in my browser I've typed that in. What actually happens? What actually happens is that it goes to our DNS server, here TAFE. Okay, we'll change this colors a little bit. So this is the TAFE SA DNS server. So hopefully everyone knows that DNS stands for domain name server. And basically, our DNS server at the TFSA is going to look in its first of all, it's going to look at this. It's obviously our DNS server is responsible for tfsa.com .edu.au. It's going to look at this and say, is this actually for my domain? Well, no, it's not. It's for a different domain name than TFSA, isn't it? So the next thing it's going to do, it's going to go through its cache. So has anyone today gone to google.com and have I looked up this particular domain name and got an IP address for it yet? If it has, so it looks, if it has, if it has, and you might have say 8.8.8. Let's say, for example, that. If it has, it's going to have this in its cache, okay? And then it just gives it back to the computer who requested it straight away. No problems, easy. But what if, now we're going to look at look up something else. What if instead of looking up google.com, we're going to look up something that's totally strange. Okay, so www.bob.com. Okay, so we're going to look up, we're going to request that in our URL. Okay, it's going to go to our DNS server here now. It's going to look in the cache. It doesn't have bob.com. Okay, it means I can't just shortcut that. I haven't looked it up today, so I just don't know it. So what am I going to do? So the process for DNS is that if our TFSA server has been configured with a forwarder, it will forward to the next DNS server. Okay, but let's say our TFSA DNS server does not have a forwarder. Okay, usually what you do is you just forward to your ISP's DNS server. That's the easiest way. It's like handball. I don't know. You deal with it. Someone else's problem. But if we haven't been, if we don't have a forwarder configured, what we do is we go to the root servers, and we'll change this color to be black. And this is signified by the dot. Okay, it all starts from a dot. So when you have a URL, whether you know it or not, there's actually a dot right at the end. All right, there's a dot right at the end. So you may not type it, but it's hierarchical. Okay, a DNS name, let's say www.tfsa.edu.au, it's hierarchical. Each dot in the middle of each one is a different level. So we go to root servers. So if you remember, we said all of these root servers are in the world. Okay, so it's not just one, it's a whole heap of them. These are their IP addresses. They exist, they're operated by various people. And basically one of these root servers, so our DNS server will go ask the root server, do you know www.bob.com? And the root server will say, no, I do not know bob.com, but I do know the DNS server, which is responsible for the top level domain .com. So, and here's its IP address. It gives that back to our DNS server. Our DNS server then will go, oh, okay, I'll go to the .com top level domain name DNS server now and ask, do you know www.bob.com? And this .com DNS top level domain name DNS server will say, no, I do not. But I do know the the DNS server which is responsible for bob.com DNS server. All right. So now it sends it back to our TFSA DNS server. And our DNS server now is going to go to the next level. Oops. Let's move this up a little bit. It's going to go to the next level. Next DNS server. All right. Sorry, so the Bob goes to the bob.com DNS server and asks the question, do you know www.bob.com? Then it's got, but this is the bob.com DNS server, and it says that yes, I do know www is an alias for SRV123. Let's say server 123. .bob.com, and then the next entry might be this SRV123. Is equal to 10.10.10.10, and then it will return this piece of information back to our TFSA DNS server, and our TFSA DNS server will put entry into its cache, which goes www.bob.com, has an IP address of 10.10.10.10, and then it will give this information to the client here. Then the client will, in the background, will use this 10.10.10.10 to get access to the resources located on www.bob.com. I know that's a little bit convoluted, and I could draw some lines, but basically, it asks the first question, and let me just change this a little bit, and then it goes to, oops, like that, and then, yep, we'll do that again, and we'll go to the root servers, then we'll go, oops, you can see I'm not an expert with these devices. It'll go to the top level domain name, and then it'll go to wrong one, and then it'll go to the specific DNS server that's for that domain. Hopefully it's that simple, and then each one is going to return some information for the next piece of the how to find the next piece, eventually finding the actual details. And that's what we've done here. Okay, so when I did NS lookup www.google.com, it went to our TFSA DNS server, and the TFSA DNS server in this case found it in its cache. Okay, because I know that because it's a non-authoritative. It means it didn't get it from the horse's mouth, if you like to think of it. I didn't get it directly from the source. I got it from checking something else. In this case, the cache. And here's the IP address. And that's how they derived that IP address. So let's get on with some of the actual theory of address resolution. Hopefully, did everyone follow me, by the way? All right, as long as you followed me, because address resolution, especially when you get to the next subject, when we go to the server subject, like no DNS, no Active Directory, basically. But that's the layer 3 address resolution. Okay, that's probably the one we have to worry about the most. But we also remember, we have the layer 2 IP addresses. Okay, MAC addresses. If you remember, we've got the ARP. And the way ARP works is that we basically just broadcast to everyone who's got this IP address. And only the computer with that MAC address replies back and says, I've got this IP address. And as a result, you put it into your ARP cache. You put it in your ARP cache, and then if you need to use it again, you use it. So let's get on with it. MAC and IP address, destination on the same network. If there are two primary addresses that assigned to a device on Ethernet LAN, so if the device is on the same network, the layer 2 physical address, which is the MAC address, is used for NIC to NIC communication on the same Ethernet network. So if we would need to find a MAC address or IP address, we can just use this MAC address on the same LAN. Layer 3, which are logical addresses or IP addresses, are used to send packets from source to device to destination device, and it doesn't have to be on the same LAN. Layer 2 addresses are used to deliver frames. Remember layer 2 frames, layer 3 packets, layer 4 segments, all those kind of things, from one NIC to another NIC on the same network. If that destination IP address is on the same network, the destination MAC address will be at the destination device. So if we look at this picture, so this is all that encapsulation we were talking about the other day. Its IP address is this. It's a class C, so the first 3 octets are the network part of it, and the last part, the 4th octet, is the host part. So if you want to think about it, the first 3 represent which network it belongs to, and the last part represents the unique individual device. So it wants to talk to this PC2, and if you look at it, IP address is 192.168.10.11. So if you remember our Boolean AND, if the /24, what do you think this /24 means?
The bar of the network.
Yeah, you're right, sort of. And let's just be a little bit more clear. So this /24 represents the length of the subnet mask, which are ones. If you remember, an IP address has 4 octets. It's called an octet because each part is 8 bits. Oct, 8, okay? So if it's a /24, it means 24 bits are used, are ones in the subnet mask. So how many octets are ones then, if it's 24 bits? 3 octets. So if the numbers in each octet are all ones, what number is that? 255. So really, what this /24 is saying, oops, go back one level. So is that annotate? So 10. What this /24 is saying, it's actually a this terrible 25. All right. Discard. I'm going to do is just yeah, I'm just going to type it here, okay? /24 really means it's a 255.255.255.0. So that /24 really represents how many of the bits in the subnet mask are all ones. So 8 plus 8 plus 8 is 24. It always is sequential. It's not like it's going to skip a spot and move to the next part. It's always in a row. So if it's 24 bits are all ones, that's basically going to give us that subnet mask. Is that enough to understand, guys? So if you remember, when we do a Boolean AND, anything that's directly above these 255s goes straight through. Okay, so the network ID for this IP address is 192.168.10 because they go straight through, and anything that's above the 0 is blocked and becomes a 0. Remember the Boolean AND when we ask is both the IP address and the subnet mask both equal to 1. Okay, and then we get the network ID for, so the network ID for this example is 192.168.10.0, because if you put this through and this subnet mask and you combine them with the Boolean AND, the 192 goes through, the 168 goes through, the 10 goes through, but the 10 over here on the above the 0 is blocked and becomes a 0. That's the network ID. Okay, so this computer network ID is that. Then it looks at is that one the same? Is that one the same? Okay, the network ID, is that network ID the same? And the answer is yes. So if that network ID is the same, it means I'm on the same local area network and this logical network. Do I need to use a router now? No. The router is only involved when you need to go from one network to a different network. So when you have the same network ID or network address, it means you belong to the same network, same logical network. Okay, is everyone following me back there, guys at the back? All good? All right. So if that's the case, if we're part of the same logical network, same network ID, if I don't need to use a router, then I just have to find out the MAC address of PC2. Okay, and we do this for ARP. We broadcast FFF, which is again all the maximum number. Okay, so remember MAC addresses are hexadecimal and FFF is the last number. So instead of actually sending it to the specific, if I don't know the MAC address, we just use a FFF broadcast MAC address. I send it to everyone that's on this LAN. It only doesn't go through to different LANs. It sticks on the same network, and only the PC with the IP address that I want to talk to will reply to that ARP request, and then from that reply, I can learn the MAC address of the destination. Then I put it in my ARP table, okay? And then I use it in my communication. You can see that the source, source MAC address is my own MAC address. The destination MAC address is the MAC address of exactly the device I'm going to. The source IP address and destination IP address are mine and the destinations. That's pretty easy, isn't it? Okay, so to communicate, I need the MAC address and the IP address of the destination. This is a little bit complicated. This is where we've got the encapsulation, decapsulation. So again, if my PC1 is this, is .10, this is this is actually expressed in a different way. So the whole network is this network ID, like we worked out just before. But this one's .10 on that network, meaning 192.168.10.10, and this is .1, which is the gateway for this network. So the gateway is 192.168.10.1. Okay, this is just expressed a little bit differently. If you're looking at this part, it's G0/0/0. So that means it's the gigabit interface 0/0/0. It's the physical interface here. And you've got its MAC address for PC1 and the MAC address of this network interface of the router one. So this is a router device, that's a switch. Switch really does nothing, just connects things together in this case. But then you notice that there's another network. So remember what I said, routers separate networks or segment networks. Every interface of a router is a different network. This is one network, this is another network, and this is another network. In this case, if you look at this, it's a /24 again, but if you notice, it's a totally different number to that, isn't it? And this middle network here, it's a totally different number to that and to that. Okay, so far so good? Everyone following me? All right, hopefully. Also, I don't want to confuse you too much more, but also I can tell from just looking at this, because we haven't covered this yet, is that these are a private LAN, because this is a private IP address. It's a Class C private IP address. This one is also a private IP address. It's a Class A IP address, but this one is a public IP address. That's something that can belong on the internet. Yep.
I'm just curious about the /30.
Yep.
So basically, instead of it being a 32 because of the 8-bit, so 4 words for the /30.
So we'll be talking about that in next week, actually.
Okay.
We'll be talking about subnetting. So for security reasons, if we actually do /30, which means there's 2 bits remaining, isn't it? So if you remember so let me get back to my thing. I'll go new. Actually, Excel is better. So just because you asked that question, not because I want to confuse you anymore, let's talk about that. So if we just look at the last octet, okay, so we all know that all of them are ones, aren't they, in the first 3 octets. So if you remember, we had 1, so that's 2 to the power, I don't know how to express this, but let's do the tilde to the power 0. Go this way. Okay. Well, let's see if we can do so this one's 2. If you remember, they're the values, aren't they? Yeah, 8. 16, 32, 64, 128, doubling each the previous one. All right. So if we have a /30, that means the first 3 octets is 24. How many more bits to get to 30? 6. So that means the first 6 of this is all ones. Okay, and these last 2 are all zeros. That's what /30 means. Okay, so that's what we call that's what we do when we subnet. We take a network and we make a smaller part of the network. It's like subdividing a piece of land. Because we remember last week we said that the IP addresses were running out. There's not enough IPv4 IP addresses. So if we've got this big giant network, why don't we just make it smaller so we can have little usable chunks? And that's why when you go to your ISP, you can buy a block of 5 IP addresses or a single IP address. Okay, but if we look at this, okay, if we look at this, really, 1 and 2. So the possibilities here are sort of, so there's really 3 possibilities, isn't there? Sorry, 4 possibilities. So basically we can go 0, we can be 1, we can be 2, we can be 3, if you know what I mean. So let's list it out. We can be 0, which we already have, which is the first one. We can be 0, 1, which is equal to 1. We can be 1, 0, which is going to be 2. We can be 1, 1, which is going to be 3. All right, so that's going to be 0. So basically, in a network that's /30, so I know this is above and beyond. I can't do it even. So if it's a /30, so we can have 4 different options in that last number. But 1 is reserved for the net ID. 1 is reserved for the broadcast, which leaves us 2 IP addresses that we can use for host. Okay, get me? So if we look at that picture now, you notice that this is here. How many hosts are on this network? 2, 1 here and 1 here. So a couple of reasons. You only need 2 because this is a point-to-point link. And so it's, for security reasons, I've only got 2 IP addresses and these 2 are using it. There's no one else needs to be on this thing. Secondly, it's a public IP address. So if I'm just using 2 IP addresses, that means that all the other IP addresses that's possible here can be used for other purposes. So that's why this is /30. But next week we'll learn exactly how we derive the /30. But hopefully what I've shown you there doesn't confuse you. It's a bit of explanation, but next week we're going to work through how we do it. Okay?
Thank you.
That's all right. So basically, getting back to where what we're talking about now. So if PC1 wants to talk to PC2, now when it does that Boolean and it works out the network ID, is it on the same network? Is PC2 on the same network as PC1? No. Then what must it use to get to that PC? Router, the default gateway here. So if PC1 wants to get to PC2, it must use this router's interface here as the default gateway. So therefore, well, the source IP address is itself and the destination IP address is PC2. That's true. But if you look at it, the source MAC address is itself, but the destination MAC address is not PC2, is it? It's actually the router's MAC address. Remember how we look at layer 2 on the LAN? When it gets to the router decapsulates it and throws it away and starts looking at the source and destination IP addresses and determines from its routing table that this is on a remote network over here, and then forwards it here. So the next step is, let's see if, oh no, it didn't go there. So let's go to the previous slide again. So the next step is now it's going to send the same frame, sorry, not the same frame, but the same information, but it's going to actually substitute the destination MAC address as the next interface, and the source adds its own. It re-encapsulates it. And then when it gets to this router, it decapsulates it again, gets rid of that frame part, looks at the source and destination IP address again, and realizes it's on this network it's directly connected to. And then the source MAC address is going to be its interface here. The destination MAC address is going to be PC2. So the IP address remains constant. The MAC address changes when you get from one LAN to another LAN to another LAN. Seriously, if you guys at the back or anyone is not following me, this is really important. Please let me know, because I can only assume if you're saying nothing, you're okay with it. All right, so that's very important, this concept, because it's going to be come up over and over again, the encapsulation and decapsulation. Okay, it's almost like, if you want an analogy, it's almost like every time it goes to a router, it's taking the envelope off the letter, writing a new envelope, and putting the letter into that new envelope. When it gets to this router, it's going to open the envelope, take the letter out, then put it into a new envelope, and send it on to this PC2. Okay? All right, let's keep on going then, if everyone's okay. ARP, Address Resolution Protocol. So ARP, like I said, is used to determine the MAC address and IP address. So a device uses ARP to determine the destination MAC address of a local device when it knows the IP address. Okay, ARP provides two basic functions. It resolves IP addresses to MAC addresses. Okay, so I need to send information to 192.168.1.7, but I don't know the MAC address basically. So what it does, it sends a broadcast to everyone, and then only the one with the correct IP address replies. Okay, broadcast MAC address is FFFFFF, all the F's, but only the one with the right IP address, because every one of the other one is going to say, no, that's IP address is not mine that I'm looking for. So this one's going to send a broadcast saying who's got the IP address 192.168.1.7, and all of these other computers are going to ignore that broadcast except for this one, which has that IP address. Then it's going to say, hey, that's me, and from that it's going to learn its MAC address from that reply, and then it's going to put it into its address ARP table with a mapping to the MAC address. So let's see if I can show you that. ARP -A. So let's look at my interface for this one. So if you remember, I showed you this previously. So this is my TFSA interface. These other ones are for various other reasons, could be virtual interfaces, but you can see that this is my router. It's got that thing. You notice that this 255 whatever, it's all FFFs because that's a broadcast. That's a broadcast IP address, if you like. This is a broadcast MAC address. And you notice that that's all I've got. Okay, so I remember for my computer, I was on a different network to all of your other computers, right? So I couldn't use ping to learn more MAC addresses because of the fact that we need to go through this router anyway. Okay. All right. So let's keep on going. So ARP functions. To send a frame, a device will search its ARP table for the destination IPv4 address and a corresponding MAC address mapping. If the packet destination IP address is on the same network, the device will search the ARP table for the destination IP address. If the destination IP address is on a different network, the device will search the ARP table for the address of the default gateway. Easy enough? So if it's on a different network, it uses the gateway. So if it uses the gateway, it needs to use the ARP table to find the MAC address of that gateway. If the device locates the IPv4 address in a corresponding MAC address, then it will use that. If it's in the table, it will use that MAC address. If there's no entry, it will do a broadcast or send an ARP request, which is a broadcast, and then it will learn it. Entries in the ARP table are not permanent and are removed when the ARP cache is timer expires. So what's worse than having no information is having the wrong information. So it only keeps it for a little bit. If it's not used or it's not refreshed, then it just leaves it. That's why you don't have a huge ARP table. The duration of the ARP cache timer differs depending on the operating system you have. ARP table entries can also be removed manually. Okay, so let's see if we can manually remove some of these things. So if I am in a Windows computer, I'm not sure what the command or the switches for the command is. I just press the /? and then it will tell me. It will give me a bit of a help. Okay, so if you look at this, A, which is what I use, displays all the entries. If I use the D, I can delete a specific host entry, and we can actually use the wildcard star to delete all hosts. Okay, let's try that then. So hopefully you all know that when I use star, it means anything. We all know that. So it doesn't matter if it's in the file system or somewhere else or programming, star in this case means anything. So if I delete star, ARP entries deletion fail, request operation requires elevation. Okay. The reason why I can't do it is because I'm just a regular user on this command prompt. So what I can do is I can actually run the command prompt as an administrator. And this is where I right-click on the command prompt and select Run as Administrator. And then it'll prompt me for this user control again. And this time you'll notice that I am administrator. I've elevated my privileges. So ARP -delete star. Now no problems. I can enter that because I'm an administrator. And let's display our. Again, you can see there's significantly less, isn't there? Okay, so if we look at this network here, you can see that we still got the gateway. I think we were using this behind the scenes, obviously, because we got that collaborate session going, and everything else is cleared. All right. So entries in the ARP table are not permanent. They can be, they expired. We can also delete them. The duration of the ARP is different. And let's see, let's look at this diagram. So media, change this text box to, I will remove the ARP entry between 15 to 45 seconds if I have not used it. So basically that's what it's saying. And the PCA's ARP table, ARP cache, should I say. All right, so here are some commands. So the show IP ARP is what you do in a Cisco IOS or Cisco router device or switch. The ARP A, -A, is what we do with the Windows computer. And these are some of the entries we see. So this is in a router, let's say, and this is in our Windows computer. Some ARP issues. ARP broadcasting and ARP spoofing. ARP requests are received and processed by every device on the local area network. So do you get that? It's like, hey, Damien. And probably every one of you guys heard me and sort of paid attention for a second, didn't you? Then you realized I was talking to Damien. Then you said, oh, don't worry about it, it's not me. Okay? But basically, all of you guys had to stop what you're doing, pay attention to me, and realize that I'm not talking to you. And that's what ARP request does to all the computers. It's pretty much saying, hey, but then it realizes that's not for me, just ignore it. So, but you know, notice that if you were concentrating on something, by me saying that, hey, Damien, you would have stopped what you did, you were doing for a little bit, so you can pay attention to me, didn't you? So if you did that, if I constantly do that, okay, if there's people, if this was a busy room and everyone's going, hey, Damien, hey, Bob, hey, Divan, hey, whatever, you would be constantly interrupted, couldn't you? Could you imagine getting your work done if you're constantly getting disrupted from concentrating on your work? It'd be very hard, wouldn't it? So that's like what the computer is going to experience if it's in a very big, busy network. In a very large network where there's like, let's look, you know how we had the /24 for Class C network, which means only the last octet was the amount of computers, which effectively can be 254 computers. 223, 0 and 225 is the two we use, so 254. Okay, so 254 type computers in that /24. But what if we had a /8? Okay, it's 254 times 254 times 254. That's a lot of computers, right? So potentially we can have really huge networks. And if we have literally calculator, if we change it to scientific, we go 254 to the power of 3. It's 16 million, potentially. Obviously not realistic, but that's possible. Okay, if you just kept on plugging in switches, plugging in uplinking switches and stuff like that, you could potentially have all these computers on the same network. Just imagine that you're in a room with 16 million people and everyone's going, hey, Bob, hey, Joe, hey, whatever. And you're having to just pay attention for a little bit every second, okay? So basically, ARP requests are received and processed by every device on the local network. Excessive ARP broadcasts can cause some reduction in performance. Obviously, you can't get your work done if you're constantly being distracted. ARP replies can be spoofed. Oh, that's a different thing. What if I went, hey, Divan, but Fee here says, hey, would that be confusing for me? If I say, hey, Divan, and Fee said, yeah, replied instead, I would start thinking she's Divan, wouldn't I? So therefore, does that mean I send all these private messages I was going to send Divan to Fee? I couldn't I, if I wasn't aware? Because if this was if we couldn't see each other and I didn't know he was Divan, I just was calling out Divan and she answered, I would start thinking she is Divan and I will send her all the important private messages. So basically, A threat actor is someone like a baddie or hacker or whatever you want to call it, performs an ARP poisoning attack. So what does that mean? They poisons your ARP, so you have to go find a new entry, and basically they spoof the MAC address, and you think they are them, and then you send them all this important information. Enterprise level switches include mitigation techniques to protect against ARP attacks. So mitigation means to reduce the impact or reduce the risk possibility. All right, let's have a look at this picture. I am PCA, and I need to talk to the router. Let's say ARP request. I need the MAC address of the default router, so default gateway, which is this over here. And so I send a ARP request. Well, this baddie guy, you can tell he's shady, sketchy. I will send an ARP reply and pretend to be the default gateway. Ooh. Okay, so basically, I media change PCC to read to red as shown, and basically we could now intercept all communications, if this worked, from the PC to the internet, because it goes to through the default gateway, couldn't it? And then what's going on with the display? I'm moving too much, maybe. Okay, is that you guys seeing lots of hands? Yeah.
It's been doing that since it started yesterday.
Sorry, guys. So I'm not. I wasn't aware of that until I just saw it on my other screen. But if I pretend to be the router, I could be what's called a man in the middle or person in the middle if I want to be PC. Because I could intercept all the information, but still keep on forwarding the traffic. So I get it, I forward it. So every time something comes through, either way, I can actually intercept it, and I can read it. If it's not encrypted or anything like that, I can read it. So anything that you might be sending, your top secret stuff, I could potentially read.